Alright, so we made balloon models yesterday to kind of show the shape of p orbitals and to show how those p orbitals fit together. But those p orbitals also fit together with s orbitals. Okay? And this requires a little bit of brain bending here. Okay? It requires a little bit of imagination. So if the nucleus of the atom is here, alright, so there's our nucleus, and the first primary energy level is the S level. Let's see. Find an orbital rotation that I've got over here somewhere. Oh, I have one somewhere. Already written out. Here we go. So here's an orbital notation. Okay. So the first energy level is the S sublevel, and the S orbital pretty much is what that S sublevel looks like. Okay. It's a sphere, and all S orbitals are spheres. We did that yesterday. So here's a sphere that represents our first energy level. Okay? There's a sphere that represents our first energy level. Okay? And we're filling orbitals. After you fill up your first sublevel with the S orbital, then you come to the second S orbital above that in the second primary level. Well, that turns out it's also a sphere. So here is the 1s orbital, here's the 2s orbital. Okay? You with me so far? Alright. Here's where it gets a little tricky. The p orbitals are inside, the p orbitals in this second primary level are inside this s orbital. They're inside there. It's like we got a big beach ball, and those balloons you made yesterday are inside the beach ball. All right, I want you to stop and imagine that for a minute, because it's really important that you can see this in your imagination, what's going on. Imagine those balloons you made yesterday. The six round balloons all tied together in the middle, okay, inside a beach ball. You got that idea in your head? Okay. All right, so we got a balloon that does this. So there's one p orbital. Here's another p orbital. Kind of running out of colors here. And so the last p orbital, so this is like on the y-axis, and this is like the x-axis. We labeled those yesterday, x and y, remember that? Okay. And so z has to come out toward you and away from you. Okay? So I mean, that's kind of hard to draw, but here's what I'm going to do. Here's how I'm going to represent that. I'm going to show one of the z coming out here toward you like that, and the other we're going to tuck in behind here, okay? Because it's back in there behind everything, okay? Does that make sense? Sort of, kind of? Maybe? Does that making some sense to you, what's going on? Okay. It's a lot going on there, isn't it? And that's only the first two levels. Okay. After that, you get to the third level, and you have to tie all those orbitals in there inside all of this. Okay? And later, you have to put d orbitals inside that third primary level. So it gets kind of complex. We're going to stop with just S and P, okay, in this class at this time, okay? Just S and P. Does that make sense? Now, when we get to the third level, it's just going to be a bigger circle or sphere representing the S sublevel, and the P orbitals are going to be like balloons in there too, just like the double balloons, okay? So the shape of them doesn't change. It does if you start trying to figure out d orbitals. That becomes more complex. And in college, you'll expect, if you take a chemistry class in college, a general chemistry class, you'll probably be expected to understand that. But for now, this is what you have to know. Does that make sense? You just have to, I want you to think about the fact that we got another level above that with S and P orbitals, another one above that with S and P orbitals, and so forth and so on. That makes sense? Yes or no? All right. So electrons, when we talk about orbitals, that's sort of a holdover from the Bohr model of the atom, where Bohr thought that the electrons were actually moving in orbits around the nucleus like planets around the sun. Bohr's model is often called the planetary model. What we found, though, is that electrons don't actually exist in those circular orbits. They exist in these regions, okay? It's a whole different kind of behavior that's kind of strange. And the only way we can get two electrons in the same orbital with the opposite spins, we've talked about that, right? Did we talk about opposite spins yesterday? No? Did we do orbital rotation yesterday? Okay. So these up and down arrows, they represent the opposite spins of electrons. Two electrons have the same charge. Particles with the same charge don't generally like to be together. Particles with the same charge tend to fly apart. All right? And the way that you can get two electrons in the same orbital, in the same general area of space, is by them having opposite spins, because it cancels their electromagnetic repulsion. Opposite spins of electrons cancel their electromagnetic repulsion. Okay? Opposite spins of electrons cancel their electromagnetic repulsion. But once you put two electrons in the same orbital, they're not paired for life really, but they're paired together until you do something to make them change. Even if I take one of these electrons that are paired right here, and I send it across the solar system somewhere, it's still going to have an opposite spin. So they're kind of somehow together even though they're apart. You can separate them as far as you want, and they're still somehow together even though they're apart. And that's something they call in physics quantum entanglement. Okay, all these subatomic particles and subnuclear particles, things that make up neutrons and protons and stuff, they have this thing called quantum entanglement. It's really cool stuff when you start to get into it. So anyway.